Most of us don't really think much about airplane engines. Honestly, who would even consider that, right? Sometimes when we are on a plane, we see the engines hanging under the wings, powering the aircraft. And in that moment, we might think about how incredible physics is and how unbelievable it is that these engines, along with such a massive amount of metal, manage to push and carry everything at such high speeds and altitudes without falling apart. Then we go back to our own thoughts, ignoring that engineering masterpiece. What I want to say is that we often take airplane engines for granted, assuming they will always work flawlessly and that we will safely travel from point A to point B. And yes, statistically speaking, according to the manufacturers I'll mention in this video, as well as their reputation, that assumption is usually correct. However, a lot of hard work and effort goes into their design and production because engines simply cannot afford to fail at such high altitudes. Hello everyone. Airplane engines are designed and built very slowly and carefully, but once they are made, they go through a merciless testing process. These tests include many different challenges, and in this video you'll see what they are, and if you haven't already, make sure to subscribe, hit the bell, and let's get 3,583 likes on this video. That's it. Let's begin. First, I should mention that there are only a few engine manufacturers in the world. Most are big names: General Electric, Rolls-Royce, and Pratt and Whitney. For decades, they have been supplying engines to aircraft manufacturers. Unlike car engines, airplane engines often work for long periods in extreme conditions. Typically, a jet engine operates at maximum power for a few minutes during takeoff, then reduces power slightly for climb and spends most of the flight at cruise power, about 75% of full thrust. In military aircraft, the range of loads is even harsher due to combat maneuvers and complex evolutions. In contrast, a car engine may spend 20% of its time at 65% power while accelerating, and about 80% of the time at only 20% power while cruising. In overall aircraft reliability, the engine accounts for 50%, which is why engines are doubled. Passenger planes, especially those flying over oceans, must by regulation have multiple engines, significantly increasing reliability. The design of an aircraft engine favors reliability above all, combined with other performance characteristics. Long operation at high thrust levels and constant change in flight conditions must not compromise reliability. To achieve this, critical engine components are duplicated. Independent systems reduce the risk of complete engine failure. For example, piston engines have two independent magneto-ignition systems, and a backup fuel pump is always integrated with electric drive. Airplanes move at high speed through the air, which allows air-cooled engines to maintain optimal temperatures without heavy liquid cooling systems. This makes engines lighter. The airflow around the engine is optimized to keep temperatures stable at expected speeds and altitudes. At higher altitudes, where the air is thinner, engines need additional oxygen. Systems like turbochargers and compressors are used to provide it, the compressor being the most common solution. Engines also face enormous amounts of water in flight. That's why extreme water ingestion tests are standard. For example, Boeing engines are tested in water troughs, and General Electric pours 800 gallons of water per minute into their GEnx engines. The engine must keep working without losing thrust. This proves that engines can handle heavy rainstorms or taxing through standing water. Ice ingestion is another test. Large balls of hard ice are fired into running engines to simulate hailstorms. Engines must withstand this without catastrophic failure. And of course, bird strikes. Birds can hit cockpits or engines. Thanks to modern design, bird strikes rarely cause fatalities, except for the birds themselves. Statistically, the chance of a bird strike disabling a modern plane is 1 per billion flight hours. However, they cause about $1.2 billion in repair costs yearly. That's why engines are tested with bird carcasses. In the 1950s, the British company de Havilland developed the chicken gun, a device that shoots bird remains at engines and windshields to simulate real strikes. At first, fresh chickens were used, later replaced with frozen ones. The goal is that fan blades must remain intact after impact. One of the toughest tests is blade off testing, simulating what happens if a fan blade detaches. Engines spin at 3000 rpm, and if a blade flies out, it can destroy the entire engine and damage the fuselage. Manufacturers test this by placing small explosives at the blade root, detonating it, and ensuring the blade remains contained. True reliability testing comes when engines are mounted on testbed aircraft. Retired Boeing 747s are often modified into flying laboratories filled with sensors and computers. General Electric and Rolls-Royce both use such platforms. Rolls-Royce even spent $70 million in 2019 to acquire and modify a Qantas 747 for engine testing. Finally, when manufacturers like Airbus or Boeing launch a new aircraft, they put both the plane and engines through comprehensive test flights, ensuring performance in every condition. Because engines, simply put, are crucial, manufacturers, airlines, and passengers all demand maximum reliability. While nothing is ever 100% perfect, aviation engines are pushed to be as close to perfection as possible. And that's it for today's video.